This lesson is on linear and angular velocity. Before we talk about the velocity part though, I'd like for us to review for just a second what we mean by radian measure of an angle, because there's a point I want to make that will illustrate to you why it's so important that we work in radians for these problems. So let's just recall, to find the radian measure of an angle, you place the angle with its vertex at the center of a circle. You measure the length of the arc intercepted on the circle by the angle, and then you divide the arc length by the length of the radius. Now I've got a problem here to illustrate what we mean. Notice that I'm asking you to find the radian measure of this angle in the picture. Well, I have already placed the angle so that its vertex is here at the center of the circle. The measure of the arc that is intercepted by this angle is 12 inches. I don't know if you can see that 12 inches or not. So the arc length is 12 inches. It says to divide the arc length by the length of the radius. The radius is 6 inches. 12 inches divided by 6 inches is 2. So the measure of this angle would be 2 radians, we say. Now, here's the reason I wanted to do this, and I'm going to be a little bit more specific instead of using that symbol. I had 12 inches divided by 6 inches. Notice when you divide inches by inches, that unit of measure cancels out. And so when we say the measure is 2, though we call it radians, basically this 2 is free of any measurement in terms of like inches or feet or even like degrees. So radian measure, since it is a real number measure as you learned previously, means that we can use that to calculate with, and we don't have to worry about mixing units like we do sometimes with inches and feet and that sort of thing. Now that we have reviewed this idea of radian measure, I'd like to talk a little bit about what we mean by velocity. Now, velocity is actually a directed speed, if you will. When you talk about speed or how fast something is going, you're familiar with measuring things like, for instance, in miles per hour. So what you're measuring is a distance that is covered divided by a time period. Okay? So many miles in so many hours, and we get miles per hour. You can also, of course, measure things in feet per second or whatever. In this lesson, I mentioned that we're going to talk about both linear velocity and angular velocity. So I want us to look at a definition of angular velocity. Angular velocity, we're going to use this symbol omega here, is theta divided by t. Now this theta represents the angle, okay? And t, of course, represents time. So angular velocity is a measure of the angle that you traverse divided by the length of time. So instead of being like miles per hour, it might be radians per hour, radians per second. You'll find that sometimes we give angular velocity in other measures, and in order to use that information to work problems, we sometimes have to convert units. Now, linear velocity, linear indicating a line, is talking about not necessarily a straight line, but a distance movement. So linear velocity, we're going to use a v, and it is a distance that we cover divided by time. Now, I have an example here. Find the linear and angular velocity of the point P. So P is here. P has moved from here to here. You'll notice I've got a D here. The distance that point P has traveled is basically the arc length here on the circle. You'll also notice I have an angle theta measured right here, and I have theta is pi over 3. I've also listed here that the radius of my circle is 12 centimeters. Now what I did not put on here is any time period. So we're going to sort of leave the time period general. But I want to talk first of all about the angular velocity. the angular velocity was defined to be the angle that you travel divided by the length of time. So the angle that we traveled was pi over 3. And since we were not given the time, this might be pi over 3, and of course this is a radian measure, so it might be pi over 3 radians per minute. So since I don't know that time period, I'm just going to say per time period. Okay? Angular velocity is the angle that we traversed, pi over 3, divided by the time period, the length of time that it took us to do that. Now, the linear velocity, which we called v, is the distance that we travel divided by the time. I did not give you this distance, but if you recall, you had a formula earlier for arc length. The formula said S equals R times theta, where you're using S to indicate arc length. Now in this formula I used a D, but D is the same thing as S here. So my D is R times my theta. So my distance is my radius, 12 centimeters, times my angle, pi over 3. If you recall, when you did arc length, you were told that you have to use this angle in radian measure in this formula, and the reason is because this distance now is going to be in terms of centimeters, because this was in 12 centimeters. This is not a unit. It's a non-unit, if you will, because those units, recall, divided out. So we have 12 times pi over 3. Of course, the 3 will cancel with that 12, and we'll get 4 pi centimeters is our distance that we traveled. So our linear velocity will be 4 pi centimeters per time period, whatever that would be, whether that was an hour or a minute or whatever. I wanted to do this because what I wanted to show you is angular velocity involves the angle that you travel through divided by its time period. The linear velocity is a distance that you travel through divided by your time period. But when you're working with circular motion, this distance is basically arc length. And so that creates a relationship between linear and angular velocity. Now look at this. Linear velocity is the distance divided by the time. If you're doing a circular distance, the distance is the same thing as the arc length S. We have a formula for arc length. It's R times theta. So do you notice the progression here? Distance is the same thing as arc length. Arc length is the radius of the circle times our angle in radians. But if you notice this part right here, theta over t is our angular velocity. And so if you notice, we end up with the R times our angular velocity. So I've left out these intermediate steps and fixed you a screen here with the simplified version of our formula. Instead of using distance divided by time for linear velocity, for the most part in these problems we're going to be doing R times omega, radius times angular velocity, because that will give us that linear velocity. Now that we have looked at these definitions and ideas, let's go to some problems that we want to work. Suppose a point P is on a wheel of radius 20 centimeters and the wheel is rotating with angular velocity pi over 15 radians per second. We are to find the angle generated, that's an extra word in there, the angle generated by P in 8 seconds. We also want the distance traveled by P along the circle in 8 seconds. And finally, we want the linear velocity of P. Now, I'll uncover these parts again here in a second, but let me come back up here and let's just sort of get a picture to help us out. We have a point P on a wheel, so let's draw us a circle. Point P is somewhere on this circle, and the radius of my circle is 20 centimeters. The wheel is rotating. It doesn't say which direction. I'm just going to say, what if we're going this direction? With an angular velocity of pi over 15, and I'm going to put down radians per second just so that we're sure of our units of measure here. Now, let's look at our questions again. The first question, find the angle generated by P in 8 seconds. In other words, as P goes around, if it travels for 8 seconds, what angle would it have traversed here? Well, if I'm doing pi over 15 radians every second, then the angle, let's call it theta, would be pi over 15 radians per second times 8 seconds. We do this every second. We're going to go for 8 seconds. If you notice here, your seconds cancel out. So you have pi over 15 times 8, or 8 pi divided by 15. Now this is in radian measure, okay? Now if we'd like to know what that angle is in degrees, we can certainly convert that over. If I have 8 pi over 15, and this is radians, remember to convert, there is what? Pi radians in 180 degrees. So notice if I have radians here and radians here, then the radians cancel out and I end up with degrees. So notice in this formula here, the pi's would cancel out, and we can do a little calculating here, and I would just encourage you to get your calculator. 8 times 180, and then we'll divide by 15, gives us 96 degrees. Now, unless the problem specifically says to give it in degrees, you don't have to do that. I just kind of wanted to review this process of converting. Certainly the answer of 8 pi over 15 radians is sufficient for the angle generated by P in 8 seconds. The second part of our problem wanted to know the distance traveled by P along the circle in 8 seconds. So not only do we want to know what angle did we traverse, and let me just kind of complete that since it's 96 degrees, something like this. We've gone through this angle. What is this distance that we have traversed? Well, that's an arc length, isn't it? So for the B part, we're actually finding arc length. And again, our formula S equals R times theta. Okay, we had a radius of 20. This was in centimeters. The angle that we traverse, let's do it in radians here, times 8 pi over 15. Okay, and this is radians, right? So there's not really a unit of measure, even though we call it radians, there's really not one there. So our answer is going to be in centimeters, isn't it? Okay, so I think what we're going to do here, let's go ahead and I'm just, since we're using a calculator, we don't even really need to reduce that. 20 times 8 times pi, remember just use your pi button on your calculator and then divide by 15, is approximately, I'm going to round off here, 33.5 centimeters. Okay, now if you don't want to give just an approximate answer, what you should do here is do some reducing, like 20 and 15. You can divide both of those by 5, and I believe when you do that you'll get a 32 pi divided by 3. So you'd have a 5 divides this and leaves a 4 times the 8 is 32 pi, and 5 divides this and leaves a 3. So 32 pi over 3 centimeters is sort of your more exact answer, and then round that off. This probably gives you a little better idea of how far we're talking. Okay, so we have our A answer, the angle that we did in 8 seconds. We have our B answer, the distance that we have traveled along the edge of the circle in 8 seconds. The last part of the question wants the linear velocity of P. Now, the linear velocity, remember, we got down to that special formula, is what? R times omega. Radius times omega. So our radius is 20 centimeters. Our angular velocity up here was pi divided by 15, and this was radians per second. Since radians is basically a non-unit, notice we're getting centimeters per second here. Now, if we just reduce this, if we divide the 20 and the 15 both by 5, we'll get a 4 pi over 3 centimeters per second. Okay? Now, I want to show you, if I take 4 times pi, 4 times roughly 3.14, I'm just using my pi button on my calculator, divided by 3, that's about 4.19 centimeters per second. Notice if I take 4.19 and multiply by 8 seconds, my answer on my calculator is saying 33.52. Notice how close we are to how far we traveled in that 8 seconds just using our arc length formula. So that just verifies that we do have the correct linear velocity. Okay? Okay, well, let's look at another situation. A belt turns a pulley of radius 10 inches at 75 revolutions per minute. Find A, the angular velocity of the pulley in radians per second, and second, the linear velocity of the belt in inches per second. Now, what they're talking about is you've got sort of a round wheel they call a pulley thing, and you've got a belt that's wrapped around that. It's probably attached to something else, and as the belt turns, it turns this pulley. Okay? Now, this pulley, it says, has a radius of 10 inches. Okay? I want you to notice that it's turning at 75 revolutions per minute. Now, what does a revolution mean? It means a complete distance around. Now, this 75 revolutions per minute is actually my angular velocity, because the angular velocity is talking about how the angle is changing or how you're going around through an angle. But we want the angular velocity in radians per second. That basically means we just need to change units here. The easiest way to change units is to just kind of group these so things are going to cancel out. If you have revolutions up here on top, then you want to put revolutions down here so they'll cancel out. Well, 1 revolution in terms of radians is 2 pi radians. Notice then we can cancel those revolutions. Now, my answer here is going to be in terms of radians per minute. I did not want radians per minute, but I wanted radians per second. So I want to get rid of these minutes. Notice the minutes are on the bottom. So I'm going to put minutes up here on top so they'll cancel. 1 minute is the same thing as 60 seconds. Now you'll notice why I went this direction. I'm wanting seconds. Notice my minutes now will cancel. So when I complete this arithmetic, I'm going to have radians on top and seconds on the bottom, and I'll have radians per second. Okay, what do we have on top? We have 75 times 2 times pi. Well, 75 times 2 is 150 pi, and in the denominator I have 60 seconds. So this is 150 pi divided by 60 radians per second. Now let's go ahead. I'm going to leave the pi in the answer here, but let's go ahead and do some reducing. Notice we can divide by 10 and get rid of those zeros, and then 15 and 6 can both be divided by 3. So I'm going to get 5 pi over 2 radians per second for my angular velocity. Now that's my A part right here. The B part wants the linear velocity. As the belt goes around, see, it's going around the edge of the circle. That's linear velocity. So the belt will be traveling the same thing as the linear velocity of a point on the wheel. Okay, linear velocity is what? R times omega. So my radius was what? 10 inches. Okay, so I have 10 inches times my angular velocity. I'm going to use this radians per second thing. 5 pi over 2 radians per second. Now, since radians is basically a non-unit, notice I'm getting inches per second for my linear velocity. That's what I want, inches per second. Okay, so I have 10 times 5 pi is 50 pi over my 2. This is going to be inches per second, and of course we can reduce this. 2 into 50 is 25 pi inches per second. Now, I'm probably just going to leave the 25 pi. If you want to, of course, you can take 25, use your pi button on your calculator. It's about 25 times 3.14, so it's a little more than 75 in terms of how many inches per second the belt is going around this pulley. One of the major problems in all of these problems is dealing with the units. Okay, in the figure below, the little r, that's this one here, is 7 centimeters, and the big R, the one over here, is 12 centimeters. So you've got these two pulleys and you've got a belt coming around both of them. The angular velocity of the larger wheel, the one over here, is 120 RPM. RPM is an abbreviation for revolutions per minute. So let me write, this one has an angular velocity of 120 revolutions per minute. Okay? What we want to do is find the angular velocity of this smaller wheel. Now, what do you expect to be happening if this belt is going around here? Which one of these is going to be going around faster? Probably this one, because it's got to go around more to keep up, doesn't it? Okay, well, let's see how we're going to get to the solution to this problem. I know the radius of this larger wheel is 12 centimeters, okay? So I'm going to go ahead and convert my angular velocity here from revolutions into radians, okay? I'm not going to worry about my minutes, but 120 revolutions per minute. And since I want to go to radians, there's 2 pi radians in 1 revolution. Revolutions will cancel out. So 120 times 2 pi is 240 pi radians per minute. Okay? Now, this is the angular velocity of this wheel. As this wheel turns around, it does what? It produces a linear velocity on this belt. So we're going to get the linear velocity on this belt. Linear velocity is what? R times omega. Well, the radius was 12 centimeters times 240 pi, and radians being a non-unit, this is per minute, so we're getting centimeters per minute. Okay? Well, I'm going to go ahead and let's see, 12 times 240 is 2,880 centimeters per minute. Oh, I left my pi off. Pi centimeters. I just did the 12 times 240. Now, the reason that I wanted to find this linear velocity is because the belt is traveling the same speed here as it is here, isn't it? Same speed around. So the linear velocity of the belt is constant. That means as it goes around this smaller wheel, the linear velocity is still this 2,880 pi centimeters per minute. Since linear velocity is radius times angular velocity, I know that 2,880 pi centimeters per minute will equal my radius, and on this smaller wheel the radius is 7 centimeters times the angular velocity of this smaller wheel. Okay? I'm going to put a little subscript WS for smaller wheel. Okay? Notice I can use this formula now to solve for this omega for the smaller wheel. All I need to do is divide by 7 centimeters. So I'm going to have 2,880 pi divided by 7 centimeters. This is centimeters per minute. Notice your centimeters cancel. And so I'm going to have radians per minute here. Okay? Now, I'm almost finished. I have the angular velocity of the smaller wheel, but I have it in radians per minute, and I wanted it in revolutions. So I need to do a conversion. Let me put that, if I can get this in right here. 2,880 pi divided by 7 is radians per minute. I do not want radians, so let's put the radians down here. I want to change it to revolutions, right? Well, 2 pi radians is 1 revolution. My radians now would cancel out. So I have 2,880 pi times 1 divided by 7 times 2 pi. I think I'm going to make this a little bit easier. Notice the 2 pi would cancel here, 1,440. The pi would cancel out. So I've got 1,440 divided by 7. I don't think that's going to divide evenly. Let me just see here. No, it doesn't divide evenly, so I think I'll just leave my answer in that form. So I'm getting 1,440 divided by 7, and this is going to be revolutions per minute. Okay. A wheel of radius 25 centimeters is rotating 1,050 degrees per second. Find the linear velocity of a point on the edge of the wheel and the linear velocity of a point halfway between the center and the edge of the wheel. Well, let's draw a picture here. I've got a wheel, and the radius of my wheel is 25 centimeters. This wheel is rotating 1,050 degrees per second. I'm wanting to find linear velocities, so we're going to work with the formula. Linear velocity is r times omega. Notice, first of all, we want the linear velocity of a point on the edge of the wheel, a point right here. So a point right here, we're using the radius of 25, and I need to multiply by my angular velocity. Now remember, this 25, let me go ahead and put the units on there, is in centimeters. So I don't want to multiply degrees times centimeters. Can't do that. So I need to convert this into radians. Okay, so let's take the 1,050 degrees per second. And this time I do not want degrees, do I? I want radians instead of degrees. So think about your relationship between radians and degrees. Well, we know what 180 degrees is pi radians, don't we? Okay, so let's see, I've got 1,050 here, and we're dividing by 180. I was going to see if that divides evenly. No, it doesn't quite, so let's just do a little reducing. We can at least divide by 10, get rid of those zeros there. 105 and 18 can both be divided by at least 3, I believe. 3 will go 35 pi, and 3 here would be 6. So this is 35 pi over 6 radians per second. We're going to bring that answer here. 35 pi divided by 6. This is radians per second. Since radians is a non-unit, centimeters per second is what we're getting here. Okay? Well, let's see. 25 times 35 is 875 pi divided by 6, and this is radians, I'm sorry, not radians, excuse me, centimeters per second is my linear velocity. Now again, if I wanted to get an approximate value for that, I certainly could, couldn't I? But I think I'm just going to leave that in that form right there. Okay, so this is the first part. Now the second part wanted to know the linear velocity of a point halfway between the center and the edge of the wheel. That would be saying a point halfway here. So this point is also going around, isn't it? The only difference between calculating the linear velocity of a point here and a point here is the length of the radius. So my second linear velocity, I'm still using r omega, but instead of using 25 centimeters, I'm using what? Well, halfway between would just be 12.5 or 12.5, okay? I'm going to put it in the form of 25 divided by 2 since we've got everything else in a fraction form. So I would have 25 over 2 centimeters is the length of my radius, and then times my angular velocity of 35 pi over 6 radians per second. Okay? And so the 25 times 35 is still the 875 pi, but now I have 2 times 6 is 12, and this is centimeters per second. Okay? Find omega, the angular velocity, and v, the linear velocity, for the minute hand of a clock if the hand is 9 centimeters long. Well, if you think about a clock face, okay, and you've got a minute hand here that is 9 centimeters long. What does the minute hand do? It goes around, doesn't it? Well, let's talk about angular velocity. Angular velocity is an angle that you go through divided by a time. Well, let's think about what a minute hand does on a clock. Starts around. How long does it take a minute hand to go all the way around? Well, 5 minutes, 10 minutes, right? A minute hand goes what? All the way around in 1 hour, doesn't it? Okay? So, the angle that we go through, I'm going to say, is 2 pi radians. It goes completely around in what? 1 hour. Okay? So, my angular velocity is going to be 2 pi over 1, or just 2 pi. And that would be in centimeters, I'm sorry, not in radians per hour. Okay? Now, what about linear velocity? Well, linear velocity is r omega. My radius is 9 centimeters, and my r turned out to be 2 pi per hour. This is radians. Again, remember, it's basically a non-unit, so we're going to get centimeters per hour. 18 pi centimeters per hour. Okay? Now, if you wanted to know that in terms of minutes, since this is a minute hand, how can we change that? Well, if I don't want hours, what do? 1 hour is 60 minutes, so we could cancel those hours out, and we would have 18 pi divided by 60, and this would be centimeters per minute. Of course, we can do a little bit of reducing here, can't we? 18 and 60, we can divide both by what? At least 6, can't we? So 3 pi over 10 centimeters per minute. Okay? Now, this problem here specifically did not say what units that they wanted each of these things in. I left my angular velocity in terms of hours, but we could convert that to minutes as well. I think what you probably are noticing here, that the thing that makes a lot of these problems hard is changing your units around rather than working with just the basic formulas. So let's take a look at some more problems. The wheels of a truck are making 630 RPM, revolutions per minute, as the truck travels at 60 miles per hour. Find the diameter of the wheels in inches. Okay, now this is an interesting problem. The wheels of a truck, so we've got a circle, are making 630 RPM. That's our angular velocity, 630 revolutions per minute. Okay? What is this 60 miles an hour? Well, let's think about what's happening. As you're going along here, the points of your wheel are coming down and hitting the pavement. So basically, the 60 miles per hour is your linear velocity. So linear velocity is 60 miles per hour. Notice we're wanting the diameter. Well, let's get to the radius first, and then all we have to do is multiply by 2 and we have the diameter. Isn't that true? Since we know angular velocity, we know linear velocity, and we know the relationship. Linear velocity is the radius times the angular velocity. We can substitute in this thing and we can arrive at our answer. Now, the problem that we're going to need to do, though, is we need to get these things in units that we can deal with. First of all, we don't want to leave angular velocity in revolutions, do we? So let's look at this. We've got 630 revolutions per minute. We want to change to radians so we can use it. So 1 revolution, let's put it down here, is 2 pi radians, isn't it? That way our revolutions will cancel. So we're going to have 630 times 2 pi. So let me just come here. R, my angular velocity now, 2 times 630 is what, 1260 pi. This is radians per minute. Okay? Alright, now over here on the linear velocity. The linear velocity is in miles per hour, isn't it? Now, we can do some converting here as well before we go to this problem. One thing I might want to notice is that this is in hours, but this is in minutes. So I for sure want to get to the same unit of time. Now, the other thing I noticed, this is in miles, and I'm wanting to get to inches. So let's do a little work on this linear velocity before we put that quantity over here. My linear velocity right now is in 60 miles per hour. Now, as I said, first of all, we want to go to minutes. So I want to get rid of hours. 1 hour is 60 minutes. So now we're through with hours. You'll notice the 60s cancel, and basically what I have here is I have 1 mile per minute. Okay? Now, if I want to convert from miles, 1 mile per minute, and I want to get rid of miles. You might not know, and I don't really offhand either know how many inches are in a mile, but I do know that 1 mile is 5,280 feet. That gets rid of my miles. But I also know that 1 foot is 12 inches. Do you see how we just keep doing some canceling here? Then our feet cancel. So 1 mile is going to be 5,280 times 12 inches, and we're going to get inches per minute when we do this. So let me take 5,280 times 12, and that gives me over here 63,360, and remember this is in inches per minute. Now, we're trying to solve for R. So notice we need to divide by this quantity right here, don't we? Okay? So I have 63,360 inches, if I can write that, inches per minute. We're dividing by 1,260 pi radians per minute, and that's going to give us R. Notice when you divide, since these are both in minutes, those are going to cancel out. I'm going to have inches here. Radians is a non-unit, so my answer is going to be in inches. Okay? So let's do this. Let me just go ahead. I've got this 63,360 already in my calculator. I'm going to divide by, now I'm going to use a parenthesis. I'm dividing by the product of 1260 times pi. So I'm using a parenthesis, 1260 times my pi. I'll close my parenthesis. Dividing that into the 63,360, R is approximately 16 inches. Okay? So if my radius is about 16 inches, my diameter would be approximately 32 inches, wouldn't it? Okay? Again, the real issue here has not been the simple formula here. To find the radius, we just have to divide the linear velocity by the angular velocity. But the problem was getting our units of measure all to agree and the right things to cancel out. Find the linear speed due to the rotation of the Earth of a point on the equator. Use 3,960 miles as the radius at the equator and express the result in miles per hour. Okay, notice I'm wanting linear speed. Well, the Earth is a circle, isn't it? And the equator runs right along the center. I'm kind of showing that as the outside. Okay, he's saying that the radius of the Earth is 3,960 miles here at the equator. So if we have a point on the equator going around as the Earth turns around, we want to get linear speed, linear velocity. Linear velocity is R times omega. Well, we know the radius, 3,960 miles. So what we need is angular velocity. Well, let's think about that. He didn't tell us. But what do you know about the Earth as it spins around? How long does it take the Earth to make a complete revolution? Well, you might think about what happens. The sun comes up. As the Earth rotates around, actually the sun doesn't come up, but the Earth rotates around. And so we make what? We make one complete revolution of the Earth, what, in 24 hours, don't we? So the angular velocity of the Earth is one revolution in 24 hours. Now I'm going to go ahead and convert to radians. So I want to get rid of this one revolution is 2 pi radians. So my revolutions cancel out. So I have 2 pi over 24, which would reduce to pi over 12 radians per hour. Okay? So let's take pi over 12. This is radians per hour. And again, since that's basically a non-unit, we're getting miles per hour, which is what we wanted, isn't it? So 3,960 pi divided by 12 miles per hour. I'm going to write it that way, mph. And of course, we can get an approximate value for that. I think I will do that. 3,960 times pi divided by 12 is about 1,000. I'm just going to round off to the whole number there. 1,037 miles per hour. Okay? A satellite travels in a circular orbit that is concentric with the Earth. If the satellite's speed is 13,200 miles per hour and it orbits the Earth in 2 hours, how high is the satellite above the Earth? Use 3,960 miles as the radius of the Earth. Okay, well, let's get a picture here, and we're going to talk about, we've got the Earth. Okay, we know the radius of the Earth is this 3,960. Okay, I'm not going to write that on there, but that would be this distance. Circular orbit concentric. What does concentric mean? Well, concentric means circles that have the same center. So the center of this orbit for the satellite is the same as the center of the circle. The satellite is orbiting out here in a circular path, concentric, so it means it shares the center of the Earth. We know the satellite's speed is 13,200 miles per hour. That's linear velocity. Linear velocity is 13,200 miles per hour. Okay? It orbits the Earth in 2 hours. In other words, it does what? It makes a complete revolution. That's angular velocity. One revolution in 2 hours. Okay? How high is the satellite above the Earth? We want to know the distance from here to here. Let's just call that D. Now I'm going to use an R here for the radius of the Earth. Okay? R plus D is the actual radius of the orbit of our satellite. We already know this part, so we're trying to find this part. Okay? Now what's our relationship? Linear velocity is radius. I'm going to use a capital R here times linear velocity, or times angular velocity. Capital R for the radius. In other words, this whole distance here I'm going to call capital R. Linear velocity is in miles per hour. This is in revolutions per hour, so let's go ahead and convert this. 2 pi radians per 1 revolution. We'll get rid of those revolutions. So 2 pi radians divided by 2 hours ends up being just pi radians per hour. Okay? So my linear velocity is 13,200 miles per hour. I'm going to try to find capital R here. My linear velocity is pi radians per hour. So to find capital R, we're going to divide 13,200 miles per hour by pi radians per hour. Okay, so the hours will cancel. I'm going to get miles because the radians is a non-unit. Okay, so let me go ahead and get an approximate value. 13,200 divided by pi. I'm just using the pi key on my calculator. Is approximately, let's see what I have here, 4,002, I'm going to round off 202. Okay, 4,202. Now remember, capital R is the radius of the Earth plus the distance that the satellite is above the surface of the Earth. So what I have here is that the distance is going to be this big R minus the radius of the Earth. So see if I have room for this. 4,202 minus 3,960. Gives me about, 242, doesn't it, miles. So the satellite is approximately 242 miles above the Earth. Okay, well, I have one more problem that I want to do for you. This one's a little bit complicated or involved, so we're going to take our time going through this and see if we can figure everything out here. A bicycle is driven by the pedals, which are attached to the sprocket wheel, which has a diameter of 10 inches. A chain connects the sprocket to a smaller cogwheel, whose diameter is 3 inches. The wheel is fastened to the bicycle's rear wheel, whose diameter is 22 inches. Find the speed of the bicycle in miles per hour when the sprocket is making 1 revolution per second. Notice the S there. Let's see if we can get sort of a picture. Most of you are familiar with the way a bicycle is set up. You've got your little circular, what he's calling here, the sprocket wheel that has your pedals on it. Here's your pedal that you're going around. You've got a chain that's attached to a smaller wheel he calls the excuse me, the sprocket. Okay. And this smaller wheel is attached to the rear wheel of your bicycle. Okay? So you kind of get the idea? Okay, let's think about what we know. Okay. It's driven by the pedals, attached to the sprocket wheel. The diameter, let's be careful here, diameter of 10 inches here. Well, if the diameter is 10, then the radius is 5, right? Okay, so the radius of this one is 5. The chain connects to the sprocket, this thing right here, to the cogwheel here. This has a, again, diameter of 3. So this small one right here has a radius of 3 divided by 2. I'm just going to leave it as 3/2 inches. Then this little cogwheel here is attached to the rear bicycle wheel, and the diameter again of this rear wheel is 22 inches, which means the radius would be 11. Okay? Now I've got everything in terms of radius, and notice everything is in terms of inches. Okay? We are looking for the speed of the bicycle in miles per hour. We want velocity, linear velocity in miles per hour. So we've got some conversions here that we need to make. Now let's talk a little bit about general ideas here before we get started. These are kind of like an earlier problem that we did. These wheels will have different angular velocities, but as this chain goes around, the linear velocity of that chain is the same. Okay? This smaller little cogwheel here is attached to the rear wheel, so it goes around in terms of an angular velocity the same as the rear wheel does. So the big rear wheel and this little cogwheel will have the same angular velocity. Okay? So we're going to sort of take this stuff a little at a time. We're going to start with this thing, which our pedals are turning. Okay? We know the radius is 5 inches. Okay? And notice also it's driven by the pedals attached to the sprocket wheel. So this thing right here is the sprocket. And notice the sprocket is making 1 revolution per second. So starting with this wheel right here, the angular velocity is 1 revolution per second. Now we know we want to get rid of revolutions. 1 revolution is 2 pi radians. Okay? I think right now that's the only conversion that I'm going to make. So I have 2 pi, the revolutions cancel, 2 pi radians per second. Okay? stay with me here. We're still working on the sprocket, so let me label this sprocket. The linear velocity of the sprocket is its radius times its angular velocity. Okay? So its radius is 5 inches. Its angular velocity is 2 pi radians per second. So I have 5 times 2 pi is 10 pi. Since the radius is a non-unit, that's inches per second. Okay? So we have the linear velocity of this sprocket wheel. Let me scoot this up just a little bit so we can keep that picture. Remember I said that the linear velocity here is going to be the same as the linear velocity on this little bitty cogwheel because they're both sharing this chain. So let's talk about the cogwheel. We know, again, linear velocity is r times omega. We know its linear velocity is going to be this 10 pi inches per second. What else do we know? We know the radius of that little bitty thing is the 3/2. 3/2 inches times its angular velocity. Okay? So to find the angular velocity of this little cogwheel right here, we're going to divide 3/2 inches into this linear velocity. Notice when we divide, the inches are going to cancel out, so I'm going to go ahead and do that. So dividing by 3/2 is like multiplying by 2/3. So 2/3 times 10 pi, the inches are going to divide out. We're going to get seconds is our angular velocity. And since all the units cancel, this is radians per second. Okay, so what do I have? The angular velocity is 20 pi over 3 radians per second. Now this is the cogwheel. But as I mentioned earlier, this little cogwheel is going around at the same angular velocity as our big rear wheel. So let's come back, scoot this up, and now we're going to talk about the rear wheel. The rear wheel is going to have this same angular velocity. The linear velocity is going to be r times omega, right? Okay. Notice that I'm looking for the speed of the bicycle. That would be my v. I'm looking for v. Well, my radius on this big wheel is 11 inches, and my angular velocity, we got 20 pi over 3 radians per second. Okay? So 11 times 20 is going to be what? 220 pi over 3, and notice that's a non-unit, so that is inches per second. Now I have the speed of the bicycle, but I have it in inches per second. I want the speed in miles per hour, so all that's left is to do some converting. Okay, so let me come down here. I've got 220 pi over 3 inches per second. Okay, let's work on this first. Do I want inches? No. So I know a conversion here. There are 12 inches in 1 foot. That'll get rid of my inches. But I still don't even really want feet, do I? So what is the conversion here between feet and miles? 1 mile is 5,280 feet. So then the feet cancel out. Okay, so I've gotten to miles. But notice I have seconds. I don't want seconds. So what can I do here? There are 60 seconds in 1 minute. So seconds are gone. But I don't want minutes. So there are 60 minutes in 1 hour. Minutes are gone. Now if you look at what I've crossed out up here on top, what I have left is what? Miles. And in the denominator, as far as units, what I have left is hours. So I'm going to get miles per hour. So let's sort of get this stuff together here in a more organized fashion so that we can just go to our calculator then. What do I have left? I have 220 pi times 60 times 60. It's 220 pi times 60 times 60, and this is miles. On the bottom, I have 3 times 12 times 5,280. See the numbers 3, 12, 5,280, and this is in hours. So I'm going to get miles per hour here. Okay? Now that we've got this, let's go to our calculator. So we can do the numerator, 220 times the pi times 60 times 60. Let's just go ahead and hit equal and get that answer. Now we're going to divide by this product, so let's be careful here. Hit your divide, but let's use a parenthesis. We're dividing by 3 times 12 times 5,280. Close your parenthesis, hit your equal. So this is going to be approximately 13.1 miles per hour. Boy, that one was kind of long, wasn't it? The key things, though, are to think about as all of these wheels are turning. What do they share in common? If they're sharing a belt or a chain, then they have a linear velocity in common. If they're going around at the same rate, then they share an angular velocity. And then the rest of the problem, other than using your linear velocity as r times omega, you have to use that idea of canceling out those units that you don't want and converting to others, and sometimes that gets strung out long. But the good thing is with the calculators we can calculate that pretty easily. This completes the lesson on linear and angular velocity.